Hello everyone, welcome and thank you for listening to my presentation. I am Ahmed Nasser al-Batrawi, presenting our work on secrecy performance analysis of ambient backscatter communication assisted mobile edge computing system with backscatter device selection. This paper is submitted to VCC 2025 and this work is under supervision of Associate Professor Ahmed Abdel Malik and Professor Sharif Rabia and Professor Wahid Zahra. The outline for our presentation, we start with an introduction explaining the background-related work, motivation, and contribution of our work. Then we explain the considered system model. After that, we investigate the system success probability analysis. Then we present some numerical results and end with conclusion and the future work. The massive deployment of Internet of Things has become essential in different disciplines, such as agriculture, logistics, smart cities and buildings, monitoring and control, and many other disciplines. However, there are challenges to achieve this massive deployment, such as spectrum scarcity, limited energy resources, limited computational resources, and security threats. Therefore, different technologies have appeared to handle these challenges. For example, for spectrum scarcity, ambient backscatter communication can achieve both spectrum efficiency and energy efficiency. It's spectrum efficient because the backscattering device exploits the surrounding radio frequency signals like from TV, Wi-Fi, and LoRa, and modulates its data on these carrier signals by tuning its antenna impedance. Therefore, it's also energy efficient because it saves the energy needed for generating his own carrier signals. Mobile edge computing also provides a solution for devices with limited computational resources. These devices can offload their computationally intensive tasks to be executed remotely at MEC servers and then get the results back. From security perspective, due to its broadcast nature, wireless communication is vulnerable to security threats. However, devices with limited computational capabilities can't apply complex cryptography techniques to ensure security. Therefore, physical layer security provides a complementary approach by exploiting the random nature of wireless channels. It has been proven that physical layer security is achieved if the legitimate channel conditions is better than the eavesdropper channel, which isn't always guaranteed. Therefore, different physical layer security techniques are used to impose that condition. Therefore, in our work, we are interested in the secrecy performance of ambient backscatter assisted mobile edge computing systems, which has been considered in literature as follows. Some papers has considered the ambient backscatter communication mobile edge computing systems without considering their physical layer security. Others have considered the physical layer security of mobile edge computing systems without considering the ambient backscatter communication. Most of the considered problems were mainly optimization problems, not performance evaluations one. And moreover, most of them have considered really fading assumption was a special case. In this work, we aim to fill some of these gaps by considering the physical layer security of ambient backscatter communication mobile edge computing networks, considering the computational benefit to the cooperative jammer. Our contributions can be summarized as follows. Investigating the security performance of ambient backscatter MEC systems with multiple backscattering devices over Nakagami M fading channels and proposing a backscattering device selection scheme. Closed form expressions for system success probability and asymptotic system success probability are derived to evaluate the system performance, and their accuracy is verified using Monte Carlo simulations. And we study the effect of different system parameters on the system performance. Therefore, our considered system model. Therefore, our considered system model consists of an access point with powerful computational capabilities, a legitimate user offloading its computational intensive and latency intensive tasks to the computational access point with energy constraint on its offloading power, and has a quality of service requirement on its offloading. We also have multiple backscattering devices offloading their tasks to the computational access point and must finish its offloading within the legitimate user offloading time and tries to secure the legitimate user transmission. We have a passive eavesdropper trying to overhear the transmission of the legitimate user. We consider Nakagami fading model, which generalizes the relay fading assumption and can model the fading in both line of sight and non-line of sight environments. Hence, the channel power gain is gamma distributed with the following BDF and CDF, and the backscatter device with the best jointed channel conditions is selected. By the jointed channel, we mean the channel from the legitimate user to the backscattering device and from the backscattering device to the computational access point. The best backscattering device is selected using the maximum selection criterion. And for performance evaluation, we use the system success probability metric from reference 6. It considers both the rate of the backscattering device and the secrecy rate of the legitimate user, which we consider in the interference limited scenario for mathematical tractability. And success occurs when these rates exceeds the predefined target rates. The legitimate user target secrecy rate depends on a quality of service requirement, while the backscattering device target rate depends on the legitimate user target secrecy rate, because the backscatter device offloading time must be equal to the legitimate user offloading time. The total probability law is used to consider all the backscattering devices. Then, for computing the probabilities I1 and I2, the cumulative distribution function of the ratio of gamma random variables and the max-min of gamma random variables is obtained. Then, with some mathematical manipulations, we get the final closed form expression for the system success probability, where the measure G function and the generalized bivariate measure G function appear. Also, some integrals were approximated using the Chebyshev-Gauss quadrature. We also obtained the asymptotic system success probability expression, where at very high signal-to-noise ratio, the system success probability becomes independent of the signal-to-noise ratio. For numerical results, we consider the effect of different system parameters on the system success probability. The following simulation parameters are used unless otherwise specified. Monte Carlo simulations of 10 to the power 6 iterations are used to verify the accuracy of the derived closed form expressions. In the first figure, the impact of the computational access point CPU frequency on the system success probability is investigated for different number of backscattering devices and channel conditions. We can find that increasing the computational access point CPU frequency increases the system success probability because the tasks of the legitimate user is more likely to be executed at the computational access point within the time delay constraint. However, at higher values of CPU frequency, no significant enhancement occurs due to the energy budget. Better channel conditions for both the legitimate and jamming channels enhances the SSP due to the higher signal to interference and noise ratio received as the computational access point and due to the higher interference on the eavesdropper. Increasing the number of backscattering devices also increases the system success probability because it's more likely to choose a backscattering device with better channel conditions. We can also notice that the derived closed form expressions matches well with the Monte Carlo simulations, which verifies the accuracy of the mathematical analysis. In the second figure, we investigate the effect of the legitimate user offloading energy budget on the system success probability. Increasing the legitimate user offloading energy budget increases the system success probability. And at higher values of the energy budget, the system performance is constrained by the legitimate user delay constraint and by the CPU frequency of the computational access point. Therefore, no further enhancement can occur. And decreasing the task size of the users increases the SSP because the likelihood of offloading and executing smaller tasks within the same time constraint increases. In the third figure, we investigate the effect of the time delay constraint of the legitimate user on the system success probability. Increasing the delay constraint increases the SSP because the likelihood of offloading and executing user tasks within the time delay constraint increases. However, at higher values of delay constraint, the performance is constrained here by the energy budget. This figure shows also that our proposed scheme achieves better performance than the round-robin and random selection schemes, even with fewer number of users. The last figure shows the effect of the signal-to-noise ratio on the system success probability. For a given number of backscattering devices, increasing the signal-to-noise ratio or the backscattering device reflection coefficient increases the system success probability because the likelihood of achieving the target rates increases. The effect of number of backscattering devices here depends on the value of the signal-to-noise ratio. For a given beta, for example, at lower values of signal-to-noise ratio, increasing the number of backscattering devices increases the SSP, because it increases the likelihood of selecting a backscattering device with better channel conditions and hence achieving the target rates. However, at higher values of the signal-to-noise ratio, increasing the number of backscattering devices decreases the system success probability. This is due to the increased interference from the backscattering devices on the legitimate user transmission at the computational access point. Therefore, a careful choice of the number of backscattering devices, reflection coefficient, and signal-to-noise ratio is critical for the system performance. This figure also validates the accuracy of the asymptotic system success probability expression. Finally, we can conclude that in the ambient backscatter communication-aided MEC networks, backscattering devices can gain a flooding opportunity while providing security for the legitimate radio frequency source transmission against eavesdropping. Increasing the number of backscattering devices isn't always a good decision. It may cause extra interference on the legitimate user transmission and reduce the system success probability. This depends on the signal-to-noise ratio and the backscattering device reflection coefficient. Using the max-min selection scheme can achieve better performance than the round-robin and the random selection strategies. Closed-form expressions for system success probability and asymptotic system success probability have been derived for the interference-limited scenario over Nakagami M fading channels, and they have been validated using Monte Carlo simulations. And for future work, we can consider ambient backscatter communication mobile edge computing networks with multiple antenna nodes and investigate also other physical layer security techniques and consider also the effect of imperfect channel estimation on the system performance. Thank you.